So moving on now in our fluid dynamics exploration, let's look at external flow. In particular, we're going to look at where lift and drag come from. I should note this is purely conceptual. You're going to see some math, but you don't need to worry about it directly. I just want you to soak in these ideas to have a little bit more awareness of where this all comes from. So the question that we want to ask is, where do lift and drag actually come from? And the answer is from two things. One is pressure force, and the other is from friction. We call that viscous forces here in our class. And so first let's look at pressure forces for a minute. What happens, for example, if you flow over an airfoil, is that the air on top goes faster and the air on the bottom goes slower. That's the basic idea. And the Bernoulli principle says that as the velocity goes up, the pressure goes down. Or conversely, if the velocity goes down, the pressure goes up. And so we have low velocity, high pressure on the bottom, high velocity, or low pressure on the top. One of the things to keep in mind is that pressure always acts normal to the surface. And so if we took a bunch of infinitesimal areas, dAs, all the way around our wing here, and multiplied them by the pressure, that would give us the magnitude of the force acting on that little area. And so there's a little bit of a force acting right here. One of the questions is, what direction does that force go? And so mathematically what we do is we define a normal vector, which there's a normal vector for every dA. Every single little one of these areas has a normal vector, and it's pointing straight out normal to the surface. And so because of that, we know the pressure is pushing inward on the surface. We're going to put a minus sign in our equation and drop this normal vector in. And so if we were to integrate this expression now, we would get the vector force acting on this surface by integrating these little teeny pressure forces with little teeny direction vectors all the way around the surface. And that's what you see here with this integral. Now you would need the pressure and the normal the pressure and the normal vectors as functions of position, and that's kind of tricky math. So thankfully we're going to do this conceptually, but we'll save that for the computational fluids folks to actually work out. Viscous forces are basically the same idea. That's the second class of forces that occur. Instead of integrating little normal vectors here though, what we're going to do is we're going to have little shear stresses, and little shear stresses times little areas become little forces. Although the shear stress has a direction as well, it just happens to be along the surface, and so we'd need a vector that gives the direction along the surface as well. Once we're done, we'd have two forces, right? A force from the viscous effects and a force from the pressure effects, and they would be vectors, and you could add those together to get the net force acting on this airfoil. What's interesting is that that force would probably be pointing upwards and to the right, kind of in this direction. And what that's a combination of is the lift force, which is pulling upward on the airfoil, and the drag force, which is trying to slow it down, it's pushing against it. It's important to keep in mind that there are drag forces associated with pressure, like this one here, as well as with shear. It's not just the friction that causes drag, there's a thing called pressure drag. And so to keep this easy, we're going to talk about drag as being the force component that opposes motion. In other words, it's in the same direction as the flow. On the other hand, the lift component is the force that's normal to the drag that's pushing upwards. And so we have drag in the direction of flow, and we have lift normal to the flow. We can get a little fancier with this by thinking in terms of these little teeny areas and just come up with the idea of how this would look. You could imagine that along the surface we have this little teeny dA, we have this little teeny pressure force vector, right, with the normal and all of that, and you'd have to add this up a bunch of times. And the math gets kind of messy, and thankfully we're going to skip it because this is normally done by computational folks. But this is how it works. And so when you start opening up these packages that will calculate lift and drag on airfoils and other shapes for you, keep in mind this is the math that's happening under the hood.